Welcome to Module 8. This module focuses on tides. Here we have a lovely photograph, once again taken from the International Space Station, showing a tidal flat in the Caribbean. You see the nice tidal channels. They look like a tree coming up and branches coming off of the tree onto sort of that lighter blue area, which is a tidal flat. In this lecture, we're going to talk about what is the tide. We talked a little bit about tides when we did the lecture on waves. We know that a tide is a type of wave with a wavelength that is equal to 1/2 of the Earth's circumference. We're going to talk about the celestial bodies that play a role in the generation of tides, what role does the sun and the moon play, and how tides are created. We'll talk about fluctuations in tidal levels worldwide, as well as looking at a subject called amphrodomic points, which discusses and explains how tides can be higher, how tide levels can be higher in one part of the planet as opposed to other areas on the planet. The final thing I want to say before we start looking at tides in greater detail is that tides are part of what we consider coastal processes. Processes that include waves and current activity that help reshape the coastlines that we see throughout the world. This slide gives a really nice definition of what a tide is. A tide is a periodic, short-term change in the height of the ocean surface. This is a change that we can actually predict. We can use mathematical models. We can say, okay, at this point in the day, at this location on the Earth, the tide is going to be at this height. We also know that a tide is caused by a combination of the gravitational force of both the moon and the sun, as well as the Earth's motion. And here we see some really excellent images of the fortress of Mont Saint-Michel in France. Very classic image that we see when we discuss tides. At high tide, it is impassable to get to the fortress. At low tide, you can very easily access the fortress walking across what we term the floor of the ocean. So this slide just shows once again the tidal range, in this case the tidal range closer to home in New Brunswick, Canada. And you can see in the upper left when the tide is in and the lower right when the tide is out. And we know that tides occur on all coastlines. The other question is though, do tides occur on lakes? And for the most part we don't see a tide on lakes. Lake Superior, sometimes people will say that it has a tide. Lake Superior is one of the largest lakes in the world. But due to changes, variations in weather and barometric pressure, this tidal change that we do see on Lake Superior is so small that it becomes almost negligible. If you remember back to the start of this lecture, I mentioned that tides are an example of a wave. In this case, the tide is a wave that always needs to operate under the disturbing force that it creates it. In this case, gravity is the disturbing force that creates this wave, the tide, and we always need gravity in operation in order for it to continue to move. So once again, we consider tides to be a forced wave. And as I said also at the beginning of the lecture, the wavelength, we know that all waves have a wavelength. The wavelength of a tide is 1/2 of the Earth's circumference, or roughly 20,000 kilometers. The final thing I want to say before we move on and talk about what actually causes the tide, something that I really want to stress is that a tidal wave is not a tsunami. So quite often in popular culture, such as movies, sometimes on TV, we see things that occur. People say, oh yes, a tidal wave took out this town, or a tidal wave caused this disaster. It is not a tidal wave, it's a tsunami. Remember, they both have different sources, or they're both generated by different events. A tsunami is generated by, for example, an earthquake under the ocean, a volcanic eruption under the ocean, whereas the tide is the result of the gravitational attraction between the Earth, the moon, and the sun, as well as the Earth's rotation. So as I've already stated, the main cause of tides is the gravitational pull, or the gravitational attraction that exists between the sun, the moon, and the Earth. Additionally, we have inertia playing a role as well. And inertia is the result of the Earth's rotation as it rotates around its axis every 24 hours. So in a couple of minutes, we'll talk about the gravitational pull that exists between the moon and the sun and how that results in tides. But first of all, we want to take just a little quick look at inertia. And inertia is a result of the Earth orbiting around the center of mass between the moon and the Earth. We're going to talk about what that center of mass is and where that center of mass occurs, and we're going to talk a little bit about what the effects of inertia can be as well on the world's ocean. So we're going to forget about the sun for a moment, and we're just going to focus on the Earth and the moon. And what we want to know is, where is the center of gravity between the moon and the Earth? So as the moon orbits around the Earth and the moon is rotating, the Earth is rotating, where is that center of gravity? And we find that the center of gravity isn't in the middle of the Earth. It isn't somewhere in space between the Earth and the Moon, but it actually occurs in the Earth about 1,700 kilometers from the surface. So if you look at the mass of the Moon, and we look at the mass of the Sun, and we look at the center of that mass, we find it sits there at the barycenter. And every 27.3 days, the Earth-Moon system revolves around that center of mass. So that's one important thing to remember, that that center of mass between the Earth and the Moon system is slightly offset from the middle of the Earth, doesn't sit in space, still sits in the Earth, and that has to do with the fact that the Earth's mass is so much greater, in fact, 81 times greater than the mass of the Moon. In the previous slide, we talked about how we're looking at the Moon and the Earth and the center of gravity between the Earth and Moon system. The Sun as well plays a role in tides on the planet. But the important thing to remember is even though the Sun is huge, it's about 27 million times more massive than the Moon, the fact that the Sun is so far away from the Earth, and you can see the distances there on the screen, means that the influence of the Sun is much less than that of the Moon. In fact, it's about 46% that of the Moon's influence or gravitational attraction on the Earth's ocean. So we'll primarily focus on what happens, that interaction between the Moon and the Earth, and then we'll throw in what happens when we add the Sun to that equation. How does that affect tides as well? We can look at tides, we can study tides mathematically. For example, we can calculate the tide generating force. What is generating the tides? What is that force? By using this equation, T equals G brackets M1, M2 over R3, where T is the tide generating force. That's what we're trying to figure out. G is a gravitational constant. M would be the mass of the Earth and the Moon. And then R is the distance between the centers of the body. So not the distance between the barycenter and the Moon, but for example, the distance between the center of the Earth and the center of the Moon. So this is one way that we can look at tides and talk about how tides are generated. We can even do some very in-depth mathematics to look at the tides and the influence of the Sun and the Moon on the Earth and the ocean and the Earth and how tides are generated. But as we'll see in the next slide, this is not how we're going to look at tides. Be aware that oceanographers do use mathematical models to study tides. Mathematics is a great tool for studying the ocean, but in the case of this course, we're not going to focus on the math behind tides and how tides are generated. Instead, what we're going to do is we're going to talk about inertia, and we're going to talk about the gravitational attraction between the Moon, the Sun, and the Earth, and look at how that plays a role. Look at more of a graphical representation of how tides occur. So the first thing is inertia. And sometimes when you hear people talk about rotation of the Earth and the role that the Earth's rotation plays in the generation of tides, they'll refer to centrifugal force. That isn't always correct. What we are talking about here is inertia. And inertia is the tendency of a moving object to continue in a straight line. So some of you might have already experienced inertia. It's what happens when you're driving down the road really fast, very quickly, and you try to go around a curb, and you can kind of feel your body shifting to the outer part or the outer side of the car. Usually if you're turning left, it'd be to the right hand side of the car. That's inertia. Your body still wants to keep traveling in a straight line, but because of steering, you're now moving the car in a different direction. The same thing happens when we look at the interaction between the Earth and the Moon. So in the very first frame of this 3-frame image here, we have a picture of the Sun in the middle there, and we'll say a planet such as the Earth there in the upper right hand corner. If a planet is not moving, if a planet is stationary in space, what happens is that the gravitational attraction between the Sun, which typically is much, much greater in size or in mass than a planet, will eventually pull that planet into the Sun. But if we go to the next frame, B, if the planet is moving, so we know that the Earth orbits the Sun, then inertia will keep that planet moving in a straight line. So we can imagine that this planet just wants to keep traveling a straight line out into space, getting further and further and further away from the Sun. But the Sun, because of its great mass, is going to assert a gravitational attraction on the planet. So the planet's trying to move due to inertia, move in a straight line. The Sun is attracting that planet, trying to pull it in, and as a result, you get that orbit occurring around the Sun. This is why the Earth travels a fixed path around the Sun. So you get the combined effect of motion due to gravity and motion due to inertia. So what happens as a result of inertia? That movement of the Earth as it rotates around, orbits around the sun, what we end up seeing is that due to inertia, we get this bulge of water that occurs on the Earth. And this bulge of water occurs on the side of Earth that is opposite the side that the moon is on. So it's on the side of the Earth furthest from the moon. One of the reasons why we see this bulge occurring on this side of the Earth as opposed to the other side of the Earth is that although the moon, as we'll see in a second, has a gravitational attraction, is trying to pull water towards it, on this far side of the Earth, the force of inertia is much greater than the force of gravity. So we get what we call an inertial bulge occurring on the side of the Earth furthest from the moon. On the side of the Earth that's closest to the moon, though, we still have inertia acting, and the inertia is trying to keep the water in place on that side of the Earth. But what happens is the gravitational attraction of the moon is much greater. So this causes another bulge of water to occur on this side of the Earth. This is known as a gravity bulge. One other thing I want to note here is if you look in this slide and the previous slide, you'll see that red dot, and that once again indicates where the approximate location of the center of that Earth-Moon system is. So let's put it together. Here we have a very simple cartoon. What we see is the Earth, and we see this big pink sphere around it. We see here the result of two bulges of water. The bulge of water on the side of the Earth closest to the moon, which is due to gravitational attraction. Once again, inertia is acting that side, but the force of inertia is less than the force of gravity. Then on the far side of the Earth, away from the moon, we see that we have that tidal bulge that's created due to inertia. And you can kind of get a sense now how we have this wave. You can think of the crest of the wave corresponding to the top parts of the tidal bulges, and then the trough of the wave corresponding to, on this diagram, it would be the north and south pole. So this diagram shows what's happening from the previous slide in a little bit greater detail. Once again, the question is, wouldn't the gravitational attraction from the moon still attract water on the opposite side of the Earth? Once again, we have to consider the two forces that are causing or resulting in these bulges of water. Gravitational attraction as well as inertia. And inertia is going to be the same for our particles on Earth, but gravity, we're going to see, it decreases as we increase the distance from the moon. So water particles or water molecules on the far side of the Earth are further away from the moon than water particles on this diagram here, what would be on the right-hand side of the Earth. So what we get here is tractive forces. These are forces. This is net force of where we combine the effects of inertia and gravity. And we can see if we look at number 1 in the upper right-hand corner of the diagram, gravitational attractions, the brown arrow, inertia is the dashed blue arrow, that the gravitational attraction far outweighs that of inertia. So inertia has a negligible effect on that side. Gravitational attraction of the moon, between the moon and the Earth's water, has a far greater effect. And then once again, we move to the opposite side of the Earth, and we find that inertia, once again, that dashed blue line, that force is much greater than what we see on the side of the Earth closest to the moon. We also see there's at one point, which ironically is in the center of the Earth, the point at which inertia and gravity or gravitational attraction are equal in strength, but travel in opposite directions and completely balance themselves out. So then the next thing you have to look at is, how do we explain this? Once again, this is an image that's taken from along the Bay of Fundy, either in Nova Scotia, New Brunswick. The location escapes me at the moment. But why do we get periods of time, or during the day or night, when the water levels are high, and periods of time when the water levels are low? For example, if you look at this very brief tidal chart on the right-hand side, we see that there's times of the day when we have what we call high tide, and times of the day that we have low tide. So how do we explain this? Looking at those two bulges of water that are created by gravitational attraction and inertia. So what is going on here? Why do we get this times during the day when we might have high tide and times where we have low tides? Well, one of the things we have to look at is we have to think about the fact that water is fluid, and that the two bulges, the inertial bulge as well as the gravitational bulge, will always stay aligned with the moon as the Earth rotates. And once again, that's because of the fact that the water is a fluid. So let's take a look at this here. What we can simply say is that the Earth rotates under the water bulges. We have these two water bulges created, and the Earth is simply rotating underneath it. So if we look at my first example here, we have a little rubber duck. We're looking down in the earth. We're standing sort of above the North Pole. We're looking straight down in the earth from above. And we have the little duck here. At time 1, T1, which would be midnight, we see that the duck is stuck on the beach. The beach is dry. It's not underneath water. And that's a time of low tide. We're sort of in that trough of that huge wave that is half the circumference of the world's ocean. Or of the world itself, sorry, but the world. So the Earth continues to rotate eastward. What happens is that duck is going to, at one point, at 6:13 a.m., it's going to be in an area where water levels are high. It's going to be sitting where that water bulge is. So now that island that was exposed at midnight is now underwater, submerged. The duck is floating, and we can say that it's a happy little duck. We are now at time 3, T3, about 12 and a half hours since we started this little experiment here. Our duck, once again, now is sitting on the beach. He's stuck on the beach. Water levels are low again. So we're in a period of a low tide at this time. And if we go forward another roughly 6.5 hours now, it's getting towards evening. We're at time 4, and we see that the duck, once again, is sitting in one of those areas where we're underneath that bulge of high water. The Earth is rotated to the point now where the duck is underneath the second bulge, the inertial bulge. It's on the side of the Earth opposite the moon. So once again, we have a very happy little duck here. He can float around and do what little yellow floating ducks are supposed to do. And then we wait another 6.5 hours now, and we see that the duck, once again, now it's about 50 minutes after midnight. The duck is sitting there. He's sad. He's tired. He's stuck on land. Once again, we're in an area of low tide. The Earth has rotated to a point where now that island that the duck lives on is exposed. It's above the water level.